Welcome to the PrepNet, presented every Sunday at 6 p.m. Eastern Time on Talk2Me's Channel 14. Come join us to discuss everything about prepping and hear what others have done. All About Electricity, Part 20, Powering My AC Stuff. Now that we have discussed batteries, battery banks, solar panels, charge controllers, and various components of a complete backup electric system, it's time to harness the electricity from the batteries and run appliances or other electrical equipment. Most people will run a DC to AC inverter to run their 120-volt AC electric equipment. But before we get to that, I wanted to explain the wiring of my system to an AC inverter. Now, the pictures you see of my wiring will appear as if I threw spaghetti against the wall. Not very pretty or well organized. Since I'm a DIY enthusiast who likes to modify or upgrade things, I work in a breadboard mode. Breadboarding is a temporary way to build electronic circuits, so it will be easy to change them. Since I know I will still make changes to this system, I have not dressed out the wiring to look pretty. My 9 280 amp hour 24-volt batteries are each connected to master bus bars using 4/0 wire, which is almost a ½ inch in diameter. The length of the cables from each battery to the bus bars is exactly the same length. This is necessary so the power is pulled from each battery equally. This connects those 9 batteries in parallel, so I have a total capacity of 2,520 amp hours, which is over 65 kilowatt hours. Because of this configuration, each battery only needs to provide a fraction of the total power needed. As an example, if my inverter is drawing 90 amps, each battery is only giving 10 amps. This stresses the batteries much less than if that 90 amps were being taken from one battery. Remember, the more you pull from a battery, the more it heats up, and heat is not good for batteries. Each battery has a large 175 amp connector to the master bus bars. This allows me to remove a battery from service for repair without having to shut down the system. It would also allow me to connect additional batteries for more capacity without disturbing a running system. The output of my MPPT charge controller is connected directly to the master bus bars by 12-gauge wire to charge them. The power from the master bus bar goes as follows. All positive and negative cables from the master bus bars are 4/0 sized cables. The positive of the master bus bar goes to a 200 amp DC breaker, which then goes to my 200 amp battery protector. Then out of the battery protector, the positive delivers the positive power to the AC inverter. The negative from the master bus bar goes directly to the AC inverter. The negative wire goes through many shunts, which are there to measure voltage and the amount of current being used. I'm not going to discuss how the shunts work or their wiring. Just trust me, they work. Finally, we have arrived at the inverters. Yes, inverters with an S. I have 2 inverters. One is a 2,000-watt 120-volt pure sine wave inverter, and the other is a 5,000-watt 120 240-volt split-phase pure sine wave inverter. First, what is a pure sine wave inverter? Aren't all AC inverters the same? No, they are not. Years ago, the first inverters, and now cheap inverters, are modified sine wave inverters. Remember from a previous net that your wall outlet AC power is a nice and smooth sine wave going from 0 to plus 120 volts and down to negative 120 volts in a nice smooth curve. However, a modified sine wave inverter creates its AC by getting to the positive and negative peak voltage of 120 volts in steps. It looks like stairs going up and then down. That's why it's called a modified sine wave. Electronics do not like this type of sine wave. They will either work badly or not work at all, and may damage sensitive electronic equipment. Using an inverter that produces a pure sine wave will give you the same quality of power you get from your wall outlet. Second, you ask why have 2 different inverters? The answer is overhead. So what is overhead? Anything that needs power to operate will consume power, even if it's just sitting there idling. This is true for your charge controller, battery protector, battery management systems, DC to DC converters, AC inverters, and meters. So my 2000-watt inverter, when turned on but I'm not running any AC loads, will consume zero point 0.3 amps or 7 watts of power from my batteries. In 24 hours, that will have consumed over 7.2 amp hours of power from my batteries and has not run a thing. The 5000-watt inverter has an overhead of 3.5 amps or 94 watts at idle. Running for 24 hours will eat up 84 amp hours of my battery bank capacity without giving me 1 watt of power to anything I want to run. That's almost 12 times more wasted battery power than the smaller inverter. Now, if I only need to run something that uses low wattage, my 2000-watt inverter can handle that, and I will not be wasting a lot of power on its overhead of 0.3 amps per hour. However, if I run that same low wattage equipment on my 5000-watt inverter, I will waste a lot of my battery power on that inverter's overhead of 3.5 amps per hour. So I use the inverter that fits my needs to be the most efficient. I do not run both of the inverters at the same time, and I only turn them on if I need them. Otherwise, they are turned off. This way, I'm not wasting power from my batteries, and the inverters will last longer. Remember, I'm not running my whole house from this emergency system. Okay, I can run my AC inverters from my battery bank, but how is that AC electricity being delivered? First, the 2000-watt inverter. This inverter has two 120-volt outlets on it. I have run a 120-volt electrical line to 3 central locations in my house to provide AC power there in times of an emergency. Each of those runs has a standard 20-amp plug on the inverter side. To power any of those locations, I just plug that line into one of the 2 AC outlets on the 2000-watt inverter. I now have AC power to that location. With this 2000-watt inverter, I can power all 3 locations with small power usage, 2 of the locations with moderate power usage, and 1 of the locations with heavy power needs. This actually fills most of my AC electric needs. Now, if I need more power to run electric tools, plus a refrigerator, and plus a microwave, or to run higher wattage equipment in more than one of the house locations, or to run my 240-volt deep well pump, I'll run the 5000-watt inverter, but only as long as I need it. So, how do I deliver the power from this larger inverter to those 3 central locations? First, the 5000-watt inverter has no 120-volt outlets. All output is through hard wiring, plus it outputs 240-volt split-phase power, just like it is into your house from the electric company. I wired the inverter's output to a split-phase breaker panel, which has one 30-amp 240-volt breaker and 4 20-amp 120-volt breakers. This gives me an extra layer of protection, just like the breaker panel in your house. But unlike the panel in your house, each inverter will have built-in overcurrent protection on the output of the inverter, plus overvoltage, undervoltage, and overcurrent protection on the DC side of the inverter. Back to the inverter breaker panel. The 30-amp 240-volt breaker is what powers my 240-volt deep well pump. The other 4 120-volt breakers power 4 different 120-volt AC outlets. 1 AC outlet for each of the 3 locations inside the house, and 1 AC outlet near the battery bank itself. This basement AC outlet is there to run any AC items in the basement. To power any or all of those 3 house locations, I plug the lead for that location into the proper outlet instead of plugging it into the outlet on the smaller inverter. The reason for the 3 different outlet circuits is to balance the 240-volt split-phase load from the bigger inverter. If I didn't balance this, the inverter would shut down due to overcurrent. The 5000-watt inverter also has 240-volt power coming from the grid, which allows this inverter to charge my battery bank with up to 60 amps going into the batteries. This is a good feature, so if I have many cloudy days and the grid is still up, I can easily top the batteries off and be ready for a power outage. I can also have my 240-volt generator charge the battery bank if needed. I don't know if you noticed, but I didn't say anything about powering lights. That's for next week, and you might find it interesting. Next week, we'll continue our All About Electricity series and discuss: why do I use 12-volt and 24-volt DC power direct from my batteries? If you have any questions about what we have discussed here tonight, please send your question to prepnetch14@gmail.com and enter question in the subject line.